Okay, so let's move to the next presenter, Dr. Qi Lei from Princeton University. So Dr. Lei got her PhD from UT Austin while working with Alex and work on fundamental, efficient and robust machine learning algorithms. She used to visit IIS and visit Simmons Institute of Theory in Berkeley, and currently she's a postdoc researcher in Princeton working with Professor Jason Lee. So please, Qi, take it over. Thank you.
Yeah. Thank you for the introduction. So I'm very happy today to talk about my recent work on Provable representation learning, and I will provide some theoretical guarantees for some specific representation learning procedures. And this is joint work with my wonderful collaborators. I will talk about both pre-training, supervised representation learning, and self-supervised learning. But I will, of course, talk about them only very high levelly. So recent years, we all see the success stories about deep learning, and many people believe their success is due to learning useful representations. And such representation can not only be learned from some supervised labels and also from self-supervised tasks, meaning that they are learned from unlabeled data. And we also hope that such representation can help us transfer to other tasks and domain, and also help us reduce sample complexity. So in this talk, in order to give some theoretical guarantees, we need to abstract the problem. So we are looking at this simple algorithm. So take multiple data, multiple tasks, and feed into the neural network. And we assume that the first few layers are shared and followed by some task-specific linear layer. So in the future, when we want to transfer the representation to the target domain, we just keep the common representation and discard the previous linear layer and only train this linear layer for the target domain. And maybe also fine-tune the representation. And we want to see if this procedure can help us. Okay, in theory, so we are trying to learn this function f, that is composition of a very simple function g with a representation phi in some function class phi. And we will have t tasks and ns samples from the source task and nt samples on the target domain. And we are interested in few shot regime, meaning ns is much larger than nt. And there is some prior work that shows the excess risk is upper bounded by the complexity of the representation function class divided by square root t plus the complexity of this final linear layer divided by nt. But in this way, you can see you cannot even use the ns samples across tasks to learn the representation. You will need a lot of target tasks, source tasks. So our goal is to look at some natural assumption such that we get some better excess risk, where we want to utilize all the samples across domains, which are ns times t samples jointly to learn this representation. And then the complexity on the target domain remains the same. And we want to design such assumptions that without these assumptions, such rate is not attainable. So compare this to the prior rate, the biggest gain is we are able to pull out ns times t samples to learn the complex representation. And the minor gain is we want to achieve a fast rate compared to the slow rate as before. And how to attain this ideal rate? So a very natural assumption is there exists a good shared representation across tasks, meaning that the labels for each task is roughly equal to a linear layer times the shared representation plus noise. So meaning that there must exist such a theta star, phi star. And also we want to assume that there is some diversity of the WT, meaning that the last layer should have some diversity in it. Why? A shared representation can help us encode what is transferred across the task. So simply put, if there is no such good representation, there's no way you can learn it, right? And also the diversity of WT, just you want to make sure it covers the final linear layer of your target task. If it doesn't cover it, you cannot learn it. Okay, so we have some result on low dimension low-dimensional representation learning. So under this kind of assumptions mentioned before, to learn such Vx, we will only need, we can show that the excess risk is upper bounded by the complexity of the representation function class divided by all the samples ns times t, plus the dimension of the linear layer divided by ns. So we will need that this k, the representation dimension, to be smaller than the number of tasks and the dimension. And also, I want to mention that covariate shift is allowed. And the role of this representation is just to select the k most important features. We also have some theoretical guarantee for high-dimensional representation learning, but due to time limit, I will not mention it in this workshop that exploits low dimensionality of neural network. Right? In many cases, there's not enough label data. Then in this case, we will want to create labels from the input data. So here comes self-supervised learning. We can also learn representations from some self-supervised learning tasks. And in this talk, I want to cover this kind of self-supervised procedure. So basically, you mask some part of the input and you predict it from the other part. And your representation will be just when you fit x2 by x1, and you learn the representation. And for downstream tasks, you will again just wrap a linear layer on top. So this kind of procedure covers context encoder, which is roughly in painting, and a BERT-like self-supervised learning. So predict missing word from the other part, and image colorization. And it is kind of mysterious how this kind of process will help you, because using the procedure, there's no extra information. We already observed the entire input. So our hope is that the representation can keep the relevant parts of y continuum x such that a simple classifier, i.e. the linear layer, will work. But how would that happen? So if you look at this kind of image, you may think about why predicting x2 from x1 will kind of help you predict y, because it's the easiest way for the learner to recover this left eye of the Pikachu is to know this is a Pikachu. The conceptual message is just reconstructing an image patch x2 from the remaining part will have to encode the information of y and some other latent variables like the subclass or some other information. We want to see what kind of assumption guarantees that. And actually this can be quantified by the conditional independence assumption, which is if x1 and x2 are conditional independent given the label and some other latent information, or in the Markov chain, it's just like this. So in this way, you can see clearly when you are able to predict x2 from x1, you have already implicitly learned the information of y and z. So with this kind of assumption, self-supervised learning can probably help you with downstream tasks. And we have shown that. So first, we want to quantify the approximate conditional independence. So we use some divergence between x2 and x1 to measure it. Let's just say this quantifies the approximate conditional independence, and also let epsilon pre just measures how well you learn the pretext task. And assume the cardinality of the latent variable z is m, and the label y's cardinality is k. Then we can show that the success rates of the whole learning procedure is upper bounded by k times m over the number of label samples for downstream tasks, plus the epsilon conditional independence and the epsilon pre. And but in comparison, empirical risk minimization will need the samples roughly equal to the complexity of the function class. However, here you only need like k times m, which is much smaller compared to any function class of interest. And we can show that x2, the image patch, does not linearly predict y, but actually the learned representation as x1 does. So in conclusion, we show that pre-training representation learning from multiple source tasks can help you learn a good representation and reduce sample complexity. We can pull out the source data to learn a complex representation, and we can handle covariate shift. I did not mention it specific. exactly, but we do. And with self-supervised learning with pretext task, the conceptual message is under approximate conditional independence reconstructing an image patch X2 from the remaining part will implicitly learn the label Y. And this can help you to learn downstream tasks with fewer samples. And in the future, we want to design some algorithm for representation learning. And also we want to do fine tuning to refine the representation error when the number of labeled samples is large. And that's all. Thank you.
Thank you. Very interesting presentation. And this time we got a few questions from the audience. Hola. Okay, so Yamini first asked, what is the complexity C5 correspond to? Could that be very high for deep neural network?
Yes, that could be very high. Yeah, I think,
okay.
But that is not something that, so that's the generalization part that is of some interest. So it's actually a kind of parallel work.
Okay,
so
Yamini,
the
do you
main
have
purpose
any
is
further?
to, yeah.
No, that's all. Thank you.
Okay, so yeah, okay, good. And Yang asked, does the low dimension and high dimension scenario share the same theory result?
Yeah, so it doesn't, it's not exactly the same. So you can imagine it by think about linear regression with ordinarily squared and with weight regression. So with ordinarily squared, you can get the result to be the excess rate is fast rate will be the dimension of the feature divided by n. With weight regression, you can achieve slow rate, which is square root of that, square root of the norm of the model divided by number of samples. So we also achieve something like that. So here, if it's high dimensional, this part will be, we have an actual square root in that, and this part will be the norm of the optimal W divided by NT, but also a square root on top. Yeah, this
Thank
just
you. And
yeah.
Thanks. And I think Qing has a last question. How strong you think your assumption for the conditional independence of data and pre-trained feature will be? Actually, I have the same question because I don't think they are really that independent.
Yeah, so actually our assumption of conditional independence given latent variable is always satisfied. You can see the only question is how large given latent variable is always satisfied. If the latent variable is, for example, x1, then of course it's satisfied. The question is only how large is the latent variable. So if the latent variable has smaller dimensionality, small cardinality, then the result will be good. Otherwise, the result will just be bad and kind of vacuous.
Oh, I see your point. I see. Okay. So if there's no more question, let's thank speaker. Thank you, Qi. Very interesting work. And let's move on to the next speaker.